Hello, hi everyone. Welcome to a new virtual tour of the European Southern Observatory, also known simply as ESO. My name is Farid Char, and with the producer Hector Salas, we are going to guide you on this journey through ESO's La Silla Observatory. So, just a little bit about me. I am one of the tourist guides, in this case for Paraná Observatory for more than 10 years. Um, I I have uh, well a lot of experience in astronomy, outreach, and education. I am also working in an astronomy center in the University of Antofagasta, and one of my main hobbies is astrophotography. So, as I told you already, I am not alone. I am with the producer, Hector Salas. So, how are you, Hector?
Hello, Farid. I'm happy to be here once again. So I'll introduce myself. I'm Hector Salas. I'm a PhD student at the Leibniz Institute for Astrophysics in Germany, in Potsdam. I work mainly with topics related to the circumgalactic medium, that is the environment that immediately surrounds galaxies. And I've been a member of the team of guides for Parallel Observatory since 2019. I started while I was doing my master's in Universidad de Antofagasta. And as Faris mentioned, today I'm going to be the producer. And that means that I'm going to be putting the videos, taking the pictures, but also I'm going to be reading all your comments. And if you have any questions, any things you want to tell us, please put it in the comment box in Facebook or YouTube. And during the tour, Farid will have a couple of breaks to answer any questions you might have.
Okay, thank you very much, Hector. So yeah, so I just want to remind you that you can send all your questions or comments through this streaming. I imagine you might already have some questions. So for this purpose, you can leave your comments or questions in the comment section on Facebook or YouTube, and Hector will be collecting all your questions and greetings, and we are going to answer to your questions during this tour. Okay. Um, Okay, so and also please don't forget to share this experience if you enjoy it, and you can share this experience just using the buttons, the sharing buttons in on Facebook or YouTube. Okay, so now let's start with this tour, and we are going to begin talking a little bit about the European Southern Observatory. So just to explain a little bit more about the organization, well, ESO is an intergovernmental organization composed by 16 member states. So its headquarters are located in Germany. Australia is also one of the collaborators here, in this case, as a strategic partner. So in this case, Chile is the host state and it's the home of to all ESO observatories. Since the 60s, and with the purpose I mentioned, ESO choose one of the best places on the planet for astronomy, for professional astronomy. In this case, the Atacama Desert in Chile. So at that time, Chile had started a site exploration campaign to attract international observatories, such as ESO, to our country. So Chile offered land, and ESO chose the area that was the most suitable for that. So the mission of ESO is to design, build, and operate astronomical observatories. And what for? To enable important scientific discoveries and foster cooperation in astronomy. Now, we are going to take a look at another picture to see the three observing sites of ESO in Chile. So first, we have the Paranal Observatory. Paranal is home of the Very Large Telescope, or VLT, and this one is right now the most advanced visible light telescope on Earth. In the future, the Paranal Observatory will also host the Extremely Large Telescope, the ELT, which will become the world's largest visible light telescope. And near there will be a CTA, an array of telescopes for the detection of gamma rays. Then we have Chaknator. This is the site of the ALMA and APEX radio telescopes. ESO participates in those radio astronomical observatories with its international partners. And finally, we have La Silla Observatory, the site you will be visiting today. This was the first observatory built by ESO in Chile, 2,400 meters above sea level, in the region of Coquimbo. So we will go there virtually during the next hour. So let's travel to La Silla Observatory. So we are going to start this trip from Germany, sorry, from Europe. So if we look at our planet, we can see that outlined in white, we can see the different ESO member states. So that's why this journey is starting in Europe. So in this case, Chile is the host country and is the home of to all ESO observatories. So to see the sites, we will travel to the Chilean mountain range. As we move over the Atlantic Ocean, let me tell you more about ESO's mission. To give you an idea, ESO tries to devise which type of instruments are needed to study the universe, and then ESO will design the pieces, will build and operate the telescopes, responding to observational requests from all the planet, and encouraging cooperation in astronomy. Okay, we are almost there. We will take a look at a very amazing mountain. So you will see a mountain range with a lot of domes in a few moments, and you need to pay attention to the shape of the hill, because the hill will remind you of something, perhaps a horse saddle. So in fact, the mountain itself and the observatory were named after a saddle for horse riding. So this was um, the final location of La Silla. So over the years, La Silla Observatory has become the perfect viewpoint for studying the universe. It was chosen by the astronomical community as an observational site at the beginning of the 1960s. Now, La Silla enjoys a large number of clear nights per year, a still and dry atmosphere, and dark skies, far away from artificial light sources, which exist in regular cities. So, the observatory was inaugurated by ESO in 1969, and some of the telescopes that we can see on in a few moments, we will see in this animation, um, are now out of service. Some of the telescopes from this video are out of service. However, we have several telescopes still working. You can see the names of the telescopes during this video. Um, and some of them are operated directly by ESO. The other telescopes, some of them are robotic. They belong to other institutions, and ESO is providing the facilities and support. So you will see the names such as the NTT, like that one over there, and you can see the CEST. This is the commissioned radio telescope, and finally you will see the largest telescope. This is the Swiss telescope, 1.2 meters, and Tarot telescope, the visitor center, and finally the ESO 3.6 meter telescope. That's the largest um, telescope in La Silla. So, okay, so now we have an overview of telescopes in La Silla Observatory. And now we are in another screen here. This is a picture of La Silla Observatory with the 3.6 meters, 3.6 meter telescope in the to the right of your screen. So we are going to start our virtual visit there. Okay. So in this picture, as I told you, we have a general view of La Silla, and I will just show you the landscape. So you can see this is the NTT, and then and there we have the other telescopes. You see, so I am going to show you the landscape. You can see that we are in an isolated place. We are far away from the cities. This is a nice view of the sunset, and you can see that we have a nice view of the mountains in the horizon. Okay, and well, this one is the CEST, it's the radio telescope, not in operation anymore. Um, and we're going to take a look at the mountains to the east. Okay, so this is basically a typical look of the Atacama Desert. Okay, so as I told you already, we are going to start this virtual experience by a chronological order of inauguration. So we are going to start visiting the 3.6-meter telescope. Okay, we're going to go inside, and here we are. So this one is the ESO 3.6-meter telescope, or 360. So the staff in La Silla is well, talking about this telescope as the 3.6-meter or the 360. So this telescope, sorry, this name, the 360 or the 3.6, is the mirror's diameter. Okay, so back in the mid 70s, it was one of the largest telescopes on the planet. Right now, it hosts an exoplanet hunter. Its name is HARPS. This is a highly specialized instrument, and we are trying to use these instruments every night to search for other planets outside of our solar system. So we are trying to look for exoplanets. So what do you notice about the dome from the inside? Well, it's huge, right? We can take a look here at the dome, and it's a big dome. So the altitude from the first floor to the dome is 25 meters. The whole structure of the telescope is equal to a 7-story building. So everything seems small here. Can you see? Um, for example, can you see a person in this picture? Well, if you haven't seen the person yet, is located there. I am going to do close up, and you can see a person here. So this is a good example to show you how big is this telescope. It's a huge telescope. It's a huge dome. Okay, so the person is below this structure, and this is a good reference to distinguish the telescope itself from the rest of this structure. So now we are going to analyze a little bit this telescope, and I am going to show you a picture. And in this picture, you can see different, let's say, portions of the telescope to explain now. So first, in dark blue, all this area in dark blue is basically the structure supporting the telescope itself. So it's basically the mounting of the telescope. Mounting works as a huge arm supporting the telescope. And this includes several systems to provide power, such as electricity. Now, on this arm, and parallel to the Earth's rotation axis, the telescope moves to follow objects in the night during the observations. Now, if we go upwards, um, in lighter blue, I mean this structure here, in lighter blue, we have the telescope's body, which holds the 3.6-meter or 360 centimeters main mirror and the secondary mirror. Now, where is the main mirror? the main mirror is it's not visible now because it's covered by its protection system. I mean this black structure. This is a system of tabs which open and close to protect the mirror from dust or moisture while the telescope is at rest. Now, in the black tubular structure here in the upper part, we have the secondary mirror, which gathers light from the main mirror and is reflecting this light to the instruments to analyze this light. Now, you will notice that the main mirror has a hole in the middle here. Okay, so basically the light is sent to the instruments through this hole. So one more time, the light is going to the primary mirror in first place. Is the light will be concentrated and will be reflected to the secondary mirror here, and the light will be reflected again, and this light is going to pass through this hole to reach the instrument. Okay, so and where's the instrument? Well, the instrument, in this case, HARPS, the exoplanet hunter, is not visible here because it's completely isolated in another room, on another floor of this building. Okay, now the 360 began operations in 1977, and from the beginning, it represented a challenge for engineering and for ESO as an organization. So European astronomy was uh, using was let's say hiring people from several countries to build an optical telescope in the 4-meter category, and the largest and most advanced category at that time. Now, why we need such a large telescope? Well, in astronomy, the objects are analyzed through this light, through its light. So the more light we collect, the more we can learn. In this case, a bigger mirror will capture more light, and therefore more information will be available. We will be able to see fainter objects and smaller details. Now, how do you think this telescope is moving at night? Well, we have a short video to show you how this telescope is moving. Hector, can we see the video? Okay, so as you can see, it's a big structure. And a mirror for astronomy, just for your information, is not just like the mirror in your homes, because the shape and surface must be perfect at the scale of fractions of thousands of millimeters. So to achieve this, in the 1970s, an extremely thick mirror was manufactured, with 53 centimeters thick on average. But this also implies an extremely heavy mirror. So the weight of this mirror is 11 tons. This is the equivalent of 2 African elephants. So if we want to build larger telescopes, we need to find other solutions. So how was the next step taken? We will see it later with the NTT. Okay. So Hector, do we have any questions so far about this telescope?
Okay, so we have a few comments, a few greetings. So give me a second. We have greetings from Sway Graven. He's on stop from Amsterdam. From I am Root. He's excited about this tour. From George, who says greetings from Mexico. From Giselle, who's watching us from Connecticut. But so far we don't have any questions. So let me ask one of the usual questions that people make. What kind of maintenance is necessary to perform on these telescopes?
Well, I can, well, if you can put the, yeah, thank you. In this a picture of the the telescope, we can see that the mirror, for example, the mirror is the most delicate part of the telescope. In order to keep the mirror in optimal conditions, we need to do some kind of cleaning, right? So this cleaning is basically a process where we need to remove dust in first place. Okay, so in order to remove dust, okay, in some cases, for example, in Prana Observatory, we are using a solution of carbon dioxide snow. This is something like a foam. Okay, so in this case, um, this is this is just we just need to rotate the mirror, the telescope a little bit, and with this carbon dioxide snow, you can remove dust. Okay, so we can keep the mirror more or less clean. Okay, and this is important because, well, this observatory is in the middle of the desert, so we have dust in the environment. Okay, now, but in order to keep the mirror in perfect shape and conditions, there is another important maintenance, and this maintenance is called recoating. So the recoating is something different because something I want to mention is that those mirrors, the surface of the mirror is a very thin layer of aluminium. So the aluminium is basically the reflective material, reflecting light. Okay, so the recoating is a process where you need to remove this aluminium layer and put a new one. Okay, so in order to do this, the usual process is to remove the entire mirror. So basically, you need to extract the mirror from the telescope. You need to move the mirror to the outside, and you need to move the mirror to another facility to do this recoating. So this recoating can take some time, of course, maybe more than one day. And when the mirror is ready, you need to bring the mirror again, reinstall the mirror in the telescope, and the mirror will be ready again for observations. Okay, so basically this is what happens here, um, and this is the necessary maintenance to keep the telescopes working in optimal conditions. And finally, you need to do this recoating system more or less every 2 years.
Okay, thank you, Fred. And another question: is it possible to visit the observatory in person?
Oh yeah, of course. You can visit Paranal and La Silla because ESO has a public visits program. So in order to visit the La Silla Observatory, you need to do an online booking, and this is important because usually when you visit Paraná or La Silla, you need to secure some slot, okay? Because we have limited spots for visiting both observatories. So, for example, La Silla has public visits on Saturdays and Sundays, and it depends on the time of the year. So, on Saturdays or all the year, you have a tour at 10 a.m. and on Saturdays, specifically from September to March, you have another tour at 2 p.m. And on Sundays, you have tours specifically from April through August at 10 a.m. So basically, the important information here is that you need to go to the ESO website. Maybe Hector, if you can please include the website in the chat section, so the people can find the public visits section there, and they can find more information about the visit in general, and they can do an online booking there. So it's completely free, but you need to arrive to the observatory in your own transportation. And for example, for La Silla, the trip from the closest city, in this case La Serena, takes more than 2 hours. It's similar to 2 hours and a half or something like that. So it's an important trip, and you need to plan in advance, of course. So let's say maybe 2 weeks in advance, at least, to do your booking, and then you can visit this observatory.
Okay, thank you. And I would like to encourage our viewers to ask any questions or send us any comments that they may have. And we'll have another round to answer any doubts you may send us.
Okay, thank you very much, Hector. So now we are going to continue, and we are going to continue to the next telescope. So we are going to visit, in this case, the NTT. So we are going to uh, go outside. We are going to return to this view, and now we can see that next to the that next to the 3.6-meter telescope, we have the NTT there. You see, this one is the new technology telescope. So the first thing I want to do is to highlight the difference between the domes. So keep in mind that both telescopes have almost the same mirror diameter. So the NTT was inaugurated in 1989. It has a small and very compact octagonal dome with a system of flaps. This represented, in its days, an evolutionary leap in the construction of telescopes, since it allowed hosting instruments in smaller and lighter structures with improved airflow on the inside. So basically, this kind of dome, like the 3.6-meter, is more something, uh, let's say, outdated. Okay, it's not the typical astronomical dome in modern observatories. Okay, so basically, this flaps system in the NTT and similar other modern observatories and domes is important and very useful to reduce turbulence and to preserve the sharpness of the pictures. Okay. Okay. So now we are going to access to this telescope. So let's enter the NTT. Here we are. So do you remember the structure of the 360, right? Well, it's huge dome and how small our the ESO person look inside. Well, in this case, for the NTT, the situation is very different because the building is practically attached to the telescope. And if we stand in front of this telescope, okay, this is the telescope, basically we will look approximately like, I don't know, like this size, more or less. Okay. So the situation is here is, of course, much more different. The telescope mounting, in this case, is also completely different. Here, the entire building spins around 360 degrees. So it's basically all of this rotating, okay? All is rotating in 360 degrees. Now, can you see the main mirror in the telescope? I'm going to do a close up. Maybe you can see that the mirror is there. Let me show you from the opposite area from here. It's the same thing, but from the opposite corner. So I am going again to do a close up, and you can see the mirror there. You see? Okay. So In this case, this disk is the mirror, and we can see that it's reflecting some light. So do you remember the 53 centimeters thick mirror of the 360? Well, in the NTT, the mirror has almost the same diameter as the 360, 3.58 meters to be precise. But in this case, is much more thin. This is a thinner mirror. The mirror is only 24 centimeters thick. It is also much lighter. In this case, the weight is something like 6 tons. So it's just like one elephant, one African elephant. Now, to keep the perfect shape as the telescope moves, there is a system of actuators or pistons. Okay, and the pistons are located below the mirror, are located here more or less, but well, you cannot see because it's covered by this structure. But we have a lot of actuators um, in this area. So the actuators are basically a kind of pistons, um, and basically we have 75 actuators, and the actuators are going up and down to keep the perfect concave shape of this mirror. So the system is controlled by a computer, and we call this system active optics. So why we need to do that? Because this kind of mirrors, when the mirror is so big, and when you need to rotate the mirror to observe different areas in the sky, the mirror can suffer deformations, distortions, just because of gravity, physics. So in order to keep the same perfect shape, the concave shape, the actuators need to go up and down in order to compensate any distortion and to keep the perfect concave shape and to preserve the quality of your final pictures. So, active optics was developed by ESO and represented a significant technological um, advantage, okay, in the construction of the next generation of telescopes in the category of in the 10-meter category, let's say. So active optics has been applied to all large modern telescopes, including the Very Large Telescope, or VLT, at the Paranal Observatory, and the upcoming Extremely Large Telescope, or ELT, currently being built near Paranal in the Armazones mountain. Okay, so now, what about the staff? What about the scientists? Well, we have around 30 people working in La Silla on different telescopes and doing different tasks. So the scientific and technical staff is working from the control room of La Silla Observatory. So basically, they are not inside of this telescope, and they are not inside of the 360. They are located in a different location, and from that location, from that control room, they are doing the remote control of this kind of facilities. Okay, so we have a short video, time lapse, to show you how the people are working from the control room in La Silla Observatory. Can we take a look? Okay. Okay, so as you can see here, this is the control room. Basically, we have two workstations. One workstation is for the NTT, and one workstation is for the 3.6 meters. So you can see that we have a lot of monitors, a lot of computers, and we have people working all night, and they are basically working in an office environment. Of course, it's very comfortable. They have all the necessary things to work all night. And usually you need a telescope operator, and you need an astronomer um, to direct the scientific observations from La Silla. Okay. Okay, I think that's all regarding this telescope, the NTT. So we are going to share with you something very interesting. Because right now you know a lot of information about the main telescopes and the staff working from La Silla. I want to invite you to see the main scientific milestones from all ESO observatories, from all ESO sites. That means from La Silla, Paranal, and Chajnantor. So, Hector, can we take a look at this video?
Observations with ESO telescopes have led to many breakthroughs in astronomy and, over the years, have been responsible for some truly remarkable findings. Here is our list of ESO's top 10 astronomical discoveries so far. Astronomers using ESO's Very Large Telescope have discovered by far the brightest galaxy yet found in the early universe, and found strong evidence that examples of the first generation of stars lurk within it, stars that were previously only theoretical. These massive, brilliant objects were the creators of the first heavy elements in history, elements that are necessary to forge the stars we see around us today, the planets that orbit them, and life as we know it. ESO telescopes have provided definitive proof that long gamma-ray bursts are linked with the climatic explosions of massive stars, therefore solving an enduring mystery. A telescope at La Silla was also able to observe the visible light from a short gamma-ray burst for the first time, showing that this family of objects most likely originates from colliding neutron stars. Astronomers using ESO's HARPS instrument in 2010 discovered a planetary system containing at least 5 planets orbiting the Sun-like star HD 10180. They also found evidence that 2 other planets may be present, one of which, if confirmed, would be among the lowest mass exoplanets ever found. Newer observations and reanalysis of the data suggest that there could be even more planets around this star. ESO's Very Large Telescope was used to detect carbon monoxide molecules in a remote galaxy, seen as it was 11 billion years ago, a feat that had remained elusive for 25 years. This allowed astronomers to obtain the most precise measurement of the cosmic temperature at such a remote epoch, and it matched the temperature predicted by the Big Bang theory. The atmosphere around a super-Earth exoplanet was analysed for the first time using the VLT. The planet, which is known as GJ1214b, was studied as it passed in front of its parent star, and some of the starlight filtered through the planet's atmosphere. The atmosphere was found to be either mostly water in the form of steam or dominated by thick clouds or haze. Using ESO's VLT, astronomers measured the age of the oldest star known in the Milky Way. At 13.2 billion years old, the star was born in the earliest era of star formation in the universe. Uranium was also detected in a Milky Way star and used as an independent estimate of the age of the galaxy. The VLT obtained the first ever image of a planet outside our solar system. The planet, which has a mass about 5 times that of Jupiter, orbits a failed star, a brown dwarf, at a distance of 55 times the average distance between the Earth and the Sun. In 2014, ALMA, the Atacama Large Millimeter Submillimeter Array, revealed remarkable details of a solar system that is forming. The images of HL Tauri were the sharpest ever made at sub-millimeter wavelengths. They show how forming planets are vacuuming up dust and gas in a protoplanetary disk. One of ESO's proudest moments came when two independent research teams, including ESO staff, arrived at a truly revolutionary finding: that the cosmos is not only expanding, but that it is doing so at an increasing rate. The findings of the separate teams were based on observations of exploding stars, or supernovae, including measurements made from ESO's telescopes at La Silla and Paranal. This discovery was rewarded with the 2011 Nobel Prize in Physics. And finally, several of ESO's flagship telescopes were used in a 20-year study to obtain the most detailed view ever of the surroundings of the monster lurking at the heart of our galaxy, a supermassive black hole. Astronomy is always moving forwards, and ESO's top 10 scientific discoveries are not set in stone.
Okay, that was a very interesting ranking of the top 10 milestones. But we have an extra result, something like a bonus track. Can you please, Hector, put this additional video? Okay, thank you. So this is something related to an important picture taken in 2019. So a team of astronomers were able to capture the first image of a black hole. In this case, this was possible with the Event Horizon Telescope, or EHT, an array of 8 ground-based telescopes distributed across the planet and coordinated by an international collaboration to achieve the first direct visual evidence of a supermassive black hole. The image will reveal the black hole at the center of Messier 87, a massive galaxy in the Virgo galaxy cluster. The black hole is 55 million light years from Earth and has a mass of 6.5 billion times the mass of the Sun. So this was the picture. Very, very interesting. Okay, so we are going to continue with the last part of this visit. And this last part is something very interesting because it's something like a virtual tour of La Silla by night. So this is a very spectacular view of La Silla Observatory during the night. As you can see, we have no moon, so we can watch the night sky in all detail. So below, to the left of the entity, we can see a very known constellation, a very well-known constellation. So this one is Orion constellation. So this one is a constellation visible from the northern hemisphere and the southern hemisphere. Okay, so Orion in the mythology is a hunter. So and the three stars here, somewhat aligned, is Orion's belt in the mythology. Okay, in Spanish, you can recognize those three stars with the name Tres Marias or Three Marys. So Orion is visible in this picture near the horizon, and you can see a very interesting object here. This object is the Great Orion's Nebula. So you can see this nebula with the naked eye, or of course with telescopes, and it's very, very impressive. Okay. Now, next to Orion, and if you look up there, we can see a very bright star, right? So this bright star, as you can see, is near Orion, and this star is actually the brightest star in the sky. This star is called Sirius. Sirius belongs to a constellation called Canis Major, and this is basically one of the hunting dogs of Orion. So basically, the constellation Canis Major in the mythology is connected to Orion. Okay, so in this case, Sirius is visible here. And as I told you already, it's the brightest star in the sky. So of course, it's very easy to recognize this star and very near Orion. So it's visible from both hemispheres. Okay. Now, as you can see, Orion and Sirius and all this area is dominated by a lot of stars, right? We have a lot of stars here. So basically, you can see a more dense area of stars if you compare with this area here or this area here. So this is because this is one of the arms of the Milky Way, our galaxy. Okay, so our galaxy is, in this case, a huge flattened disk shaped as a spiral galaxy. So in this case, from Earth, we see it as a band of light across the sky because of our viewpoint, because we are inside of this disk. So the Milky Way, it consists of around 200 billion stars and huge clouds of interstellar gas and dust. We can see some gas here with some nebulas. You see some dust formations. So of course, this is a very complex area here, full of objects, full of astronomical objects. The red clouds here, in this case, are made of hydrogen. This is the simplest and most plentiful element in the universe. Okay, and basically the stars are made of hydrogen mostly. Okay, so we continue looking at the Milky Way here, but there is something interesting. We are going to focus on something here, the horizon, because we can see two um, spots here, two spots in the sky. Those spots are the large and the small Magellanic Clouds. These are our closest neighboring galaxies. So, because they are orbiting the Milky Way, they are satellite galaxies of the Milky Way. Of course, they are not clouds, they are galaxies, as I told you already, but we call them the Magellanic Clouds because the first person to record them it was Ferdinand Magellan during its circumnavigation of the planet in the 16th century. So at that time, no one had any idea about the galaxies, so he recorded those objects as clouds. Okay, so in this case, an additional information about this is that next to the Magellanic Clouds, we have something that we call the South Celestial Pole. The South Celestial Pole is basically a projection of this geographical South Pole in the sky. So basically, during the night, all the stars in the southern hemisphere appears to revolve around this point, the South Celestial Point. So if you take a long exposure astrophotography toward this direction, you will see a lot of concentric circles. Okay, so in order to find this point, the South Celestial Pole, one of the techniques is to imagine something very similar to a triangle using the Magellanic Clouds and the South Celestial Pole as the corners of this triangle. You see, but the other way is to use the constellation here, that is the Southern Cross. This is the smallest constellation in the sky, the Southern Cross. This constellation is only visible from the southern hemisphere. It's the smallest constellation and in the sky. And in order to use this constellation to find the South Celestial Pole, we have to do something in our minds. We have to project the longer stick of the Southern Cross 4.5 times, more or less. So we have to get this longer stick and we can project this. We can project this like 1, 2, 3, 4.5, and more or less like here, we have the South Celestial Pole. As you can see, I need to use those techniques because in the Southern Hemisphere, we don't have any bright star near the South Celestial Pole. This is a difference in contrast with the Northern Hemisphere, because in the Northern Hemisphere, you have the North Star, right? Polaris. But in the Southern Hemisphere, we don't have any bright star here. So we need to use those techniques. We can build a triangle using the magnetic clouds, or we can project the longer stick of the Southern Cross, something like 4 times and a half. Okay, so that's it. And the last thing I can show you from this picture is that if we continue looking at the Milky Way, um, basically we are looking again at the 360, and we can see that next to the 360 we have the center of the Milky Way emerging from the horizon. You see, so um, we have a wider area here with a lot of different dark clouds, with a lot of gas, dust, you see. So basically, this area of the center of the Milky Way is dominated by the Scorpius and Sagittarius constellations. Okay, for example, this star here, this one with this yellow tone, is called Antares. Antares is the brightest star in the Scorpius constellation. So it's very easy to recognize, of course, the star and the constellation. But basically, the center of the Milky Way in the southern hemisphere is basically dominating the night sky in the winter months. I mean, the winter months in the southern hemisphere. I mean, June, July. So this is another difference if you compare with the northern hemisphere. Because in the southern hemisphere, you can see all the Milky Way in the sky. I mean, you can see, for example, in this picture, you can see all the Milky Way here, but in winter months it's even better because you can see the center of the Milky Way very high in the sky all night. And this is something very, very impressive, especially for people from the northern hemisphere that sometimes are visiting Chile, and they are very, very impressed because they can see all the Milky Way all night, very high in the sky. Because in the northern hemisphere is different. Okay, so that's the situation here. This was the quick tour of La Silla during the night. Just to finish, I am going to show you another view here. This is the 360 at night again. By the way, this light here is light pollution from La Serena. And this is something important also to mention. Light pollution is a big problem for astronomy. So we are trying to keep control of the light pollution from all observatories in Chile. I mean, in all the north of Chile, because this could be a big, big problem for our night skies, because this is the most important natural heritage of the north of Chile, and of course, our observatories are taking advantage of this natural heritage. Okay, so just to finish then, you can see a nice view of the telescopes of La Silla. So we are going to move to our final destination here. This is basically the road coming from the 360. Okay, so you can see all the other telescopes in this road, and eventually this road is connecting to the residence or the hotel of La Silla, because we have the telescopes, we have the control room, but we also have La Silla Hotel. And in this place, the scientists, the technicians, all the people working for the observatory can take a rest from here. So we are going there. We are going to the hotel to finish this virtual experience. Of course, we have a very beautiful sky. This picture, for example, was taken in winter because you can see all the center of the Milky Way in the zenith. You see, this is basically the usual view of the night sky in winter months. And this is a general view of the La Silla Hotel. And this person is the photographer. So basically, all the pictures you saw before were taken by this person. And he's relaxing here in the La Silla Hotel. So, okay, so this was the virtual visit to La Silla Observatory. So I don't know, Hector, if we have some last questions before finishing this.
Okay, we have a lot of greetings from Tetsuito, who says a very good program, from Michele from Venezia, from Enrico, who's watching us from England, Diego from Montevideo, from Jose Maria, and from Michael, who also asked us why in the pictures the sky looks somewhat reddish. Could you elaborate on that?
Well, probably maybe it was from the previous picture. Some of the pictures were. I think there was some kind of hydrogen clouds or something like that. Well, just to let you know, some of the pictures here, in order to get this kind of detail, this kind of colors, and to get a nice view of the nebulas, especially, probably the photographer was using some filters, okay, in order to let pass some specific wavelengths of nebulas, in order to let pass, for example, the hydrogen. Okay, so in some cases, some specific nebulas have a lot of hydrogen or have a lot of other elements. So that's why in some cases you can see this uh, reddish color because it's related to one specific element there.
Okay, thank you. And we don't have any more questions. We have one last greeting from Antofagasta. And I think it's just time to end the tour. I would like to say goodbye to everybody and wish you a nice day. Please remember that you can always go to the ESO website where you find all the pictures, videos, and 360-degree tours that you can walk at your own pace. And we're also doing virtual tours from Paraná Observatory, La Silla Observatory in Spanish and in English. So keep an eye on when the next tour is going to be in English language.
Okay, thank you. So I would like to just remind you that all the visits, information, pictures, and material is available on the ESO website. And also we have a surveys. So maybe Hector, if you can put the link, so
Yeah.
you can send your comments about this virtual experience. So we will well, wait for you for the next virtual tour. We have tours in Spanish and English, Paranal and La Silla, so you can just stay updated in the ESO social networks to know when we will have the next virtual tour. Okay, so from myself, thank you very much for yes.
Yeah. Before we go, we have one question here from George Jensen. He usually uses the doors. I want to answer it very quickly.
Yeah, sure.
So he asks us about if there are any instruments able to observe in infrared bands. The answer is yes, there are. For example, in Paranal, the Muse instrument reaches some part of the infrared, and depending on where in the infrared, it can be complicated. So you might need to be in a space instrument, so you don't get contaminated from emissions from the Earth. And for the use for narrowband filter is mostly to observe specific elements. So you, you know the wavelength at which oxygen, for example, could be emitting. So you try to observe in just that narrow band, so you can only observe the oxygen and no other elements. Or you can do the same with hydrogen or with, I don't know, magnesium or whatever. So I hope that answered a bit your question. Okay, that was it.
Okay,
All right, so
so thank you very much again, and I hope to see you again in the next virtual tour. So thank you very much, and goodbye.
goodbye.